cloud. Okay, good, great. So it's my pleasure, as suggested by Hoa, to introduce our speaker today, Andrew Eberhard. I don't think he needs big introduction. He is a long-term member of our community, and everybody on all continents knows Andrew. I can only say that he has always been a good friend of mine and also of Chao. He used to come to Ballarat on each occasion, whether it was Rubinov lecture or Chao showcase or whatever. So I've always felt support from Andrew. But it's not about research. Andrew has done a lot in optimization and has contributed to many areas of optimization. I'm very far from reciting all his biography, but I know, and everybody now knows, that he is good at building bridges. And today it is going to be about bridges between discrete and continuous optimization, and also stochastic programming. So he is trying to connect three things in one go. Okay, Andrew, the floor is yours. Please speak slowly, because I know that you like speaking very fast. If you want people like myself to understand something, speak slowly. Okay, Andrew.
Okay. Thank you very much for that, Alex. And thanks to the organisers for inviting me to give this talk. This is joint work with Brian, Fabrizio and Jeffrey, who were in a discovery grant of mine some years ago. And this sort of work began a little bit before that with some joint work with Natasha Boll at the time. It was the person who kind of got me into integer programming and made me realise, well, there was some opportunities here to do some work, given that I'd come from very much a variational analysis, non-smooth analysis background. So this is a story that sort of spans, I suppose, about 8 years, I suppose. So first of all, some background. Well, stochastic mixed integer programming, what is it all about? Well, there are decisions that are made in a model in stages, and basically there's an uncertainty about how certain parameters in the model evolve as time moves on, and as each stage is revealed, a sort of a random variable selected from a probability distribution, and this affects the kind of way that you have to make decisions to sort of make some optimal decision. And when you have discrete variables in these problems, then they become even harder, and you get this thing called a stochastic mixed integer program. And this combination of combinatorialness and discreteness makes it, in fact, a very computationally challenging problem. So this is a story about how one tries to handle these problems. Now, they have wide application, and I'm not really a sort of a major person in application. I've worked with people in applications, but this is an area which has found very wide applications. So what we have, so in a general form, what we have is it looks a lot like a linear programming problem. We have a sort of first stage variable which we'll call x, and then we have another term which depends upon x. So our first stage variables are constrained to a set x, capital X, which involve integer constraints and linear constraints. And what we have is the second term there involves the stochasticity, and I'm only going to really look at this in this talk on two-stage problems. So the second stage variables are y. They're going to have to satisfy some linear constraints, which all depend upon a random variable we'll call xi. In fact, what we do in these problems is that we try and fit a discrete distribution. So there's a kind of a modeling problem where you try to fit a discrete distribution of the data that you have to turn this into something which is then possibly computable. So for every scenario, the second stage of various scenarios, depending upon the probability distribution, there's a constraint set for the y's, and we index the y variables with S for the scenario. And when we fit a discrete distribution, which are given by the PSs, we've already got a finite number of elements in the script S set, then what we have is we can then turn this into a kind of a mixed integer programming problem. And you'd say, well, why isn't the story all over then? Can't we just put this into Groby or something and get a solution? And there you are. Well, the problem is that because the scenario tree grows exponentially, these problems in fact become very large and incapable of being solved by ordinary techniques very rapidly. And even two-stage problems are problematic depending upon the number of scenarios you have. So you have to make some assumptions, and convenient assumptions to be made is that the KS is the constraints theory we have on the scenario sets, the X's and the XS's, are only involve integral constraints and linear constraints on the variables, and they're closed and they are bounded. It's just simplifying assumptions we can make for the purpose of developing some theory. And of course, for every scenario, if we've got a first stage variable, if we're given a first stage variable, it's constrained to its constraint set here. And oops, sorry about that. I'm going to get my pen working. Its first stage constraints there. Then what we want is to find the scenario-wise constraints on the YS's, which depend upon the X's. We define them that way. And so what we have is a thing usually that we refer to as relatively complete recourse. We presume that for every first stage variable that we have, we're going to have a solution, a feasible YS for every scenario. And this is a standard assumption that's made in many models. So these problems grow exponentially, and of course this leads to the desire to look for decomposition techniques to make them solvable, and techniques we can carry out in parallel. So that's the name of the game. So as some background, the simplest things that you can do is that you can try and use some sort of Lagrangian decomposition and splitting technique to get somewhere, at least with a bound. And this is very typical in integer programming, is that if you can get some bounds, the worst thing that can happen is you can put these bounds into a branch and bound process to turn an inexact technique into an exact technique. So, so what you do is you make copies of the first stage variables, you make them scenario-wise dependent. And so for each scenario, you demand you have this feasibility. And so then you demand, of course, as a second constraint, is that the first stage variables must all agree at the first stage, because I can't have a hindsight. What I have to do is make sure that any solution I choose has the same first stage selection. And so this is called non-anticipativity constraint. We can't anticipate the what's happening in the second stage. And so what we try and do is force this constraint in some way. And one way of doing this is to just do simple Lagrangian relaxation. So here we have some multipliers. We relax this constraint. And what happens, of course, in this case is that now we get a problem that's scenario-wise decomposable. But of course, to have a solution that makes any sense, I have to have some a feasibility condition on the Lagrange multipliers so that my Lagrangian makes sense, and this follows directly from the usual conditions that you have in your Lagrangian optimality. And so therefore, if I in fact redefine my dual variables by omega s's by dividing by the probabilities, then I can actually decompose my function, my Lagrangian, into a weighted sum of Lagrangians that all decompose in a scenario-wise, they're really a scenario-wise average of these individual Lagrangians. And these individual Lagrangians must satisfy the corresponding condition for feasibility of Lagrange multipliers. So I should always choose my omegas and get a bound that's sensible by having this as a feasible dual condition. And so then what I get is then that my Lagrangian is in fact found by averaging really these individual Lagrangian problems that I have, which scenario-wise decompose. So this gives me a decomposition technique and a way of trying to find sort of a Lagrangian, or what we call a non-anticipative Lagrangian bound on the problem. So when we see for any feasible Lagrange multiplier, we get a lower bound if we've got a minimization problem for the optimal value. And this, of course, means that we can try and find the best lower bound by finding the optimal dual bound using some sort of technique to find the optimal solution to that problem there. And so that's really the state of the art, if you like, given, say, about 8 years ago, until we started looking at this problem and looking at other different methods. So this algorithm I'm going to talk about right now, the Frank-Wolf progressive hedging method, has become quite popular. And what it does is it integrates progressive hedging with the sort of Frank Wolf idea, and tries to develop a provably convergent method that's parallelizable and has some theoretical underpinning. Now, what I've done in the previous page, all we really know is that we got a bound, but we haven't said anything about how we find the solution to that bound. We need some technique here to do that. And so first of all, let's introduce this idea by first of all imagining that I knew the convex hull of the feasible set of these KSs, the scenario-wise constraint sets. And I know that I don't know these things, but I'm going to construct an approximation as we go along. And so if I presume that I've got this, if I know this, we'll call this conv SMIP, then it's just, I can apply the standard theory of progressive hedging as developed by Rockefeller and Wentz to say that if I apply progressive hedging to this problem, it's now a continuous problem. It's this continuous stochastic optimization problem. It has a fully developed theory for convergence of progressive hedging for this. So the whole problem is, of course, that I don't know the structure of the convex hull of the set I have. So let's familiarize ourselves with where progressive hedging came from. So what we have with progressive hedging is we take the augmented Lagrangian, and we really look at the kind of averaged augmented Lagrangian of the scenario-wise decomposition, where I've decomposed scenario-wise by, again, introducing this relaxation, which has the non-anticipativity constraint relaxed into the Lagrangian. So I have an augmented Lagrangian, and I could, with the augmented Lagrangian, of course, apply the ADM, and that's what it would look like, where I update my Lagrange multipliers, and I would try to apply ordinary augmented Lagrangian problems here. Now, what we do in stochastic optimization is we single out the consensus variable, and what we essentially do is we split this, and we try and do a sort of ADMM type thing, where I only minimize over the augmented Lagrangian scenario-wise for the first block, the x's and the y's, and then what I do is I effectively minimize over the z's, and of course, if I was minimizing over the average of this, of course, what I'd be doing is minimizing the dispersion, and when you minimize the dispersion, the solution of that's the average. So that's really all we're doing, is when we do the average of the z's with respect to the xk's, is in fact what we're doing is we're trying to minimize this function, the mapping of z to that Lagrangian, where I've averaged this Lagrangian. In fact, what I'm doing is actually averaging this guy with respect to z at the current xk, yk, and omega k for the current solutions. And then, of course, I'll do my multiplier update like usual. And of course, that is what we might mean by progressive hedging. And if I knew the convex hull of the solutions of the feasible set, then the ordinary sort of theory of progressive hedging as embedded in ADMM type format would apply. And I could write down a solution theorem, just picking things out of the literature. So if I knew this guy, then I'd know that things would work. I would know that my objective value would converge to the optimal Lagrangian dual bound. I'd know that my Lagrangian values, that the optimal Lagrangian variables would converge, and I know that my consensus constraints would converge in the limit. And that is just picked out of the theory by knowing that you've got a really convex optimization problem, and the usual theory applies. So now what we know, and what the situation was, say, 10 years ago, is that people took this sort of framework and they just simply applied mixed integer programming, so QMIPs, to solve the quadratic problems, and I just applied this naively to a stochastic problem and just looked to see whether they got anything sensible. And what they found is if they didn't have the penalty parameter very large, then it seemed to work. And this is a bit of a mystery for many years, is that they got convergence to a Lagrangian bound that made sense by doing something which was an heuristic that had no underpinning theory whatsoever. So what we'd like to do is try and bridge this theoretical gap here. Instead of we want to know why applying QMIPs might work. This method, of course, is pretty much a primal method, because I mean, even though really what progressive hedging is a primal dual method, if you like, because we're really trying to solve the primal and dual problem simultaneously. But when people are using these QMIPs to solve their primal problem, it's primarily, we'll call that a primal method rather than a dual method. And so Frank-Wolf progressive hedging tries to deal with this problem that we want to solve this optimization problem in progressive hedging. So what we do is we try and use a thing called the simplicial decomposition method, which is really an extension of Frank-Wolf. And in our context, it would look like this. So I'm trying to solve that problem in blue above. And so what I do is that I linearize the Lagrangian and I minimize over the convex hull of the vertices of this set. And what I do is I get, of course, I'm linearizing a linear objective over a region here. Now this guy there, I know that the vertices of this guy are exactly the same as the vertices of the original set that I had. And what I have here is a linear objective. So in fact, this problem here can be solved by solving a MIP, a mixed integer programming problem over this set with the integral constraints in it, because that will generate for me a vertex solution, because we know that minimizing a linear functional over a convex hull, well, over a discrete set, if you like, even, will generate a vertex of the convex hull. So you solve this problem by solving MIPs, and of course, they're scenario-wise decomposed, and this is a very efficient thing to do. And when I generate a vertex, then I can add it to an approximation of my vertices. And in fact, what I do is I take that collection of vertices as I go along as I iterate. So what I'm doing is iterations over t. And as the iterations increase, my inner approximation of the convex hull of Ks is going to be this convex hull of the vertices I've gathered together, and it grows over time. And so I can see that if I did this often enough, I'd wind up getting a growing inner approximation of the set that I want. Now, the truth of the matter is that I don't actually do this. I do something slightly trickier, and it's based upon this lemma. This is the critical lemma that makes this algorithm efficient. So what do we do here? I'm wanting to solve these scenario-wise minimization problems over this convex hull of this unknown set. And I'm solving these MIPs, of course, to get these vertices. And what I do is I've got this lemma that says, and we get this lemma essentially by investigating the optimality conditions of these problems. And basically, I find that if the vertex I'm generate from this solving this problem, where I've replaced this by my current approximation, my VT set, if the solution I generate in this way is not optimal, is not actually optimal for the true problem, then I know that when I add the vertices I generate, I strictly increase my inner approximation. Okay, so this is my lemma that says if the problem that I'm solving up here, this guy up here, doesn't generate me the actual optimal solution, then I know that the set that I'm generating down here will strictly increase in size. So with that lemma in hand, I can prove convergence of progressive hedging, where in fact what I do in the progressive hedging is that I replace my problem here with one iteration of this algorithm. I do one iteration. So I don't do multiple iterations, I just do one. I add one vertex every iteration of my progressive hedging algorithm, and I replace the minimization, the scenario-wise minimization problem with this linearized problem solved by using a MIP. And so I claim that that method converges. So I'll give you a proof for where I do two iterations of this simplicial decomposition, because it's simpler than the one using one, and it's a little bit too long here, but the two-step one is very straightforward. So what I have here is I claim that my inner approximation I get by adding my vertices and taking the convex hull each time increases, and eventually at some point it stabilizes at some fixed set. Why would this be the case? Well, remember my set is bounded. It has therefore only has a finite number of vertices. So I can only add a finite number of vertices. So at some point the process must halt. In fact, it halts before you add all vertices. And then what I find is that under this under the assumption, well, under my lemma I claim that what I get at the end is I get some sort of a continuous polyhedral here. It's an inner approximation of my Ks I have here. And I claim that indeed that we must therefore, by using this approximation, actually solve this problem when I do the SDM step. So I claim that my next solution will be optimal for the problem that I want. Now, why is that? Well, if it wasn't optimal for this problem here, then I know that I could add my solution, my verdicts I generate, and I would increase the inner approximation. But of course, we've already assumed that we've stabilized the inner approximation, so that's a contradiction. So if the inner approximation stabilizes, then my SDM problem actually solves the problem that I want to solve. And so therefore, the theory of progressive hedging in the continuous case then applies from there on, and I can then re-invoke the theorem I had, and everything therefore converges, because from there onwards, I'm solving the problem I wish to solve. And in fact, you can show that we do numerical experiments of this, that it actually works very, very well. And so it's actually become quite a popular technique over the last 4 or 5 years. So here's some experiments using a cluster that we have at the National Computing Infrastructure in Canberra, and we use CPLEX to solve our MIPs for the problems. And so I'm going to plot here some curves which are going to be for some standard test problems. So these are capacitated facility location problems, dynamic capacitated facility location problems, and server location problems with scenario sizes of different sizes. So we have these problems, and I'm going to show you some plots just to give you an idea of what happens when we run these various algorithms for a 2-hour war clock. And what I have here in these plots here is that the dashed ones are just ordinary progressive hedging, where I'm solving the quadratic programming problems with QMIPs and with certain penalty parameters. The solid lines are actually our progressive hedging Frank-Wolf algorithm for different penalty parameters. And we see here that for large penalty parameters, the heuristic actually starts to oscillate and doesn't reach my optimal objective value, because I have the objective value associated with the lower Lagrangian, the Lagrangian dual bound plotted here. So as for a low penalty parameter, the progressive hedging seems to do all right, but of course ours does a lot better for large penalty parameters, and we get convergence to the optimal dual bound. And in fact, in this case, actually we get the optimal value for the stochastic integer programming problem. We actually converge the optimal value here. And this is the same sort of story I get for the other kind of problems. DCAP have continuous variables in the first stage, and they don't quite converge to the optimal value. There's a slight duality gap, but we get very tight bounds and very quickly, while the heuristic has trouble for large penalty parameters. And here's another, here's the server location problems. There's the plots for those. And again, we see a similar story. So that's sort of half of the story that I want to tell, but I'm going to tell part of the another part of the story, which is about Lagrangian dual problems in integer programming. Now, there's a lot of work done about several years ago, and Natasha Boll and I published a paper in this that's got a number of people interested in this work. Of course, people in non-smooth analysis have been looking at this for a number of years. I think Regina and Alex Rubinoff did as well. But here what we have is we try and look at augmented Lagrangian using some sort of penalty for problems of this kind, where I've got a more general kind of Lagrangian problem where I'm trying to find the optimal Lagrangian value. And we want to know when I have zero duality gap for these problems. Well, I have to make some assumptions about the penalty, and we make these sort of assumptions usually. And what it means, the penalty, it looks like a norm. It looks pretty much like a norm. So if I assume the penalty is pretty much like a norm, which means it's non-differentiable at the origin, then I can state a theorem, and this is a kind of typical theorem, is that there's a finite rho value for which the augmented Lagrangian winds up giving me the optimal value of the stochastic integer programming problem if I choose the optimal Lagrangian of the linear program relaxation. And it turns out actually we can take any lambda, but the rho will depend upon the lambda. And what we're interested in here, of course, is we're interested in the case we've got the relaxation of our non-anticipativity constraint in our case. Now, it turns out that there's another way entirely of looking at these problems as a block Gauss-Seidel problem, and this is kind of the primal way of looking at the same set of problems. And so it kind of comes back to this duality problem, is that when I want to try and reinterpret progressive hedging as some sort of block Gauss-Seidel iterative, where we're doing one block which will be on the x's and the y's, and the second block on the z's, which is like we have in progressive hedging, then it would be nice to have some assurity that the Lagrangian bounds I'm generating are going to give me an optimal Lagrangian bound. And so for a period of time, we were quite interested in these duality theorems, hoping that we might get some theory here which might tell us something about why in some of these problems we actually do generate optimal values for these problems using progressive hedging in these stochastic situations. Well, this is the story about what we learned when we try to go down that path. And so this is the sort of primal story. Well, it turns out that if we're going to do Gauss-Seidel, the assumptions that we got on these penalty functions that we have, that we just stated, are not the right ones. So I'm going to postulate a different set of assumptions. And these assumptions are really designed to allow me to have something that looks more like a norm squared, where it's actually a differentiable coupling function. So this penalty function, if you go back and look at Lagrangian, what it does is it sort of couples the z's with the x's and the y's that we're generating from our scenario-wise decomposition that we have. So it's the thing that couples the z's to the scenario-wise decomposition minimization. And so what we're going to do here is we're going to assume something in terms of two variables. We're going to look at these problems where what we've got is an x and a y, and I'm going to be, in fact, talking about a kind of a regularization on these scenario-wise decomposed problems. So I'm going to have my problem here involving two variables. So it's going to start looking like a norm. It kind of monotonically increases in both variables strictly. And I'm going to assume this sort of strong convexity type property, which means that the thing that I've got looks more like a norm squared. So we're going to make those assumptions in our penalty. And then what we're going to do is we're going to take our stochastic mixed integer programming problem. And here's my objective of the original problem. Here's my constraint sets. And here's my scenario-wise decomposition. And now what I'm going to do is I'm going to add in a penalty function which tries to couple the z's to the x's and these w's to the y's. Now, the w's are introduced as a technique to make this fit the theory better, because what I want to do is I want to interpret this function I'm generating here, which is now a continuous function z and w, as being a regularization of this problem. So my problem actually has a linear objective, but the constraint sets have got integer values in it. So in fact, it's quite a lumpy problem. It's quite non-smooth. The value function is very non-smooth. It's quite staircase, in fact. But I've got this Lipschitz regularization, this smooth regularization, which is trying to create a nicer function here in z and w. And in fact, that's a Lipschitz function. So that's a Lipschitz function. And what we're going to do now is try and look at the minimization problem of this function here of phi rho. And in fact, what we're going to do, in fact, later on, we're going to be relating this to sort of the augmented Lagrangian optimal value for where the Lagrangian multipliers are actually put to 0. Now, I want to solve this problem, and I'm going to do this by doing some sort of Gauss-Seidel. So what is Gauss-Seidel? Gauss-Seidel, is what we do is we minimize in respect to one variable first to get an update, and then we put that variable back in, and we minimize with respect to the second variable to get an update on the second variable. And we iterate this way back and forward in order to try and find a solution. Now remember here, phi here is my continuous Lipschitz regularized function. And what I want to do is I want to try and reinterpret this algorithm in some way that relates to progressive hedging. So let's now go back to our scenario-wise decomposition here. Now, in progressive hedging, all I would do is I'd take this guy as being rho times by a norm squared, and then I'd get back my progressive hedging with my multipliers put to 0. So we don't have our linear term in it. So that would be my solution for progressive hedgings. Now, if I assume, first of all, that my WK update, WK plus 1, is not equal to my scenario-wise Y values, I'm going to show I get a contradiction. And so that tells me how I set my first block update. So here's my definition of what my regularized function is. Now I know that my Y star and my X star are the optimal solutions for that problem. So that's my equality. Now I'm going to use the fact that if I put this to 0, I get a strict increase by my assumptions on my penalty function, the second set of assumptions. So I've multiplied the second guy by a multiplier, which is 0, which gives me a strict inequality. And then what I do is I put in the obvious thing, the Y star S minus the Y star S gives me 0. And then what I do is I minimize over the X's and the Y's to get something smaller again. And then I reinterpret this as being this function, this regularized function. And so what I've found is that this guy must be strictly greater than that guy, which means that WK plus 1 is not the argmin of this problem. And that's a contradiction because I choose WYK plus 1 to be the arg minimizer of that problem in my Gauss-Seidel. So this is false. Those two have to be equal. So what does that tell me? It tells me that the YK plus 1 to be a solution of this, I just choose it to be equal to the solutions of this problem, the scenario-wise solutions of that problem. So I do this in blue, and my Lagrangian value is just, in fact, going to be the number 8 there. So that really means that to get the first step in the block Gauss-Seidel, all I do is do exactly what I do in progressive hedging, except with my multiplier 0. So the first block is just progressive hedging with the multiplier 0. What about the second block? Second block is doing this minimization problem. So again, let's go through and just look at what happens at every stage. So I look at my definition of what my regularized problem is. So I know that my xk plus 1, my yk plus 1 are all taken to be the solution to this problem. And now what I do is I use the fact that if I put the second guys to 0 again, and I minimize over the z's, I must get a strict inequality. In fact, that must follow because if the x's are not equal to the z's, then in fact this thing has a strict minimum, and so I get a strict decrease. And then what I'm going to do here is I replace. I realize that I can replace the 0 with wk plus 1, wsk plus 1 minus ysk plus 1, because I already know they're equal to each other from the previous argument. And then what I do is I take a minimum again over all the x's and the s's to get something smaller again. And then I reinterpret the answer here as being precisely this function here, which is from the definition of what my regularized function is. And so what have I shown by that step? I've shown that my original value goes through these decreases, these strict decreases each step. And so in fact, what I get through the Gauss-Seidel by doing this is I get a strict decrease, a descent in my regularized function. So I can reinterpret my block Gauss-Seidel as being this algorithm. The algorithm is I solve my scenario-wise problems here, and of course in progressive hedging, this is just rho times the norm squared. I call my wk plus 1 update just what I get for the yk plus 1s. I minimize my dispersion. Of course, when this is just rho the norm squared, minimizing the dispersion means I would just average, which is what I'm doing before. And then I get this, which looks like progressive hedging, but with the Lagrange multipliers all put to 0. Well, I claim that this is really almost progressive hedging, because if I go back and I look at the norm squared penalty, and then I ask the question, well, what happens if I take my penalty function, instead of just being this, but being the multipliers plus that? Well, what I can do, of course, is I can just complete the square. So I complete the square, and I get this as being my completion of the square plus some constants, which don't depend upon variables, which I'm minimizing over. And so what I'll do is I'll consider that this is my new penalty. And now I'll ask the question, what happens if I update my second block as a minimization of this dispersion, this penalty here? Well, we can minimize that. We can solve just by differentiating to find a solution. I get this, but of course, when I average the multipliers, the average of the multipliers is 0, means that the second term just drops out, because I know that my feasibility condition for the multipliers I retain all the way through with progressive hedging will just knock that out. I just get the average back again. So if I replace my penalty with this penalty, then all I'm doing is progressive hedging with that penalty. So what about looking at some further theory? Now, this comes to the part which is the work that we're just sort of finishing off now and looking at tidying up. But what we want to do is we want to provide a theoretical foundation really for the convergence of the block Gauss-Seidel iteration. So let's try and talk about doing block Gauss-Seidel on problems of this kind. And it turns out that that what we need to do is we need to look at decomposing the kind of functions, the regularized function we have in terms of its sort of constituent parts. And so what I'm going to do is I'm going to have a notation here where y sub I, x sub I, y sub I are the integral components of these guys. And so this set will just consist of the integral components. And if I fix those integral components to a fixed value and just look at the continuous parts, I'll denote that set of the continuous part of that set, like so. And so I can think of my regularized function as being composed of bits where I've actually fixed certain integer values to certain values and only allowing the continuous parts to move. And then, of course, I can write down the regularized part where I've fixed these integral values to those fixed integer values to be this function. So here's my regularization where I've fixed certain integral solutions to a fixed value. So first thing that we can notice here is that under reasonably general assumption of these guys, the assumptions that we had before, that if I look at the feasible solutions of my stochastic mixed integer programming problem, the Z's are feasible, the WS's are chosen to be satisfied the second stage feasibility, then there's some rho and some delta such that for rho bigger than that value and delta smaller than that value, my regularized function will locally look like one of these integer values valued one. Well, so these ones where the integer values are fixed. So there's a neighborhood in which these integer values are fixed. So locally around these feasible points, it looks like a smooth convex function if I fix the integral values. And moreover, in that neighborhood, this convex function has a minimum at the feasible point. So the feasible points are the local minimizers of these sections of this regularized function. Just to kind of give you an example of what goes on, here's just a toy example where I've got some values here for my k's, some linear functions. I'm using quadratic regularization. My sets only contain 4 integral points where their function values are given by this. And if I look at all the sections, I could write the sections down. They all look like that. And the local solutions of this problem actually turn out to be these guys. There are 4 of them. 2 are associated with the feasible solutions and 2 are associated with bogus local minima. The ones associated with the bogus local minima have values that depend upon rho. And you can see they increase as rho increases. So this prompts us to sort of think about our problem this way. If I look at my regularized function for a fixed value of a W and looked at how it varies with Z, if I looked at a cross section, they sort of look like this. There are these parabolas, and I'm taking the minimum of them, and I get these minimums occurring at feasible solutions and some bogus ones, but of course their values are increasing with rho. And so it can happen that I have local minima where the values of that regularized function blow off to infinity, and I can have local minima where their neighborhood of attractions shrinks to 0, which actually happens, as you can see. This neighborhood here is going to get worse as this guy goes upwards. It's going to decrease in its size. So I call a minimum persistent if its objective value is bounded above for all rho, and I have a family of persistent local minima if they converge to some fixed value, and they persist as rho goes to infinity. And so what we're going to do now is think about Gauss-Seidel. This is what Gauss-Seidel does. It tries to descend an objective by doing it component-wise. And we know that Gauss-Seidel, from the theory of Gauss-Seidel, we know that it produces a partial minimum, a Z star and a W star satisfying these guys. But unless we have some other assumptions, we don't know whether that's actually a local minimum. And we're interested in the local minimum because they're going to give us the feasible points. So this is when we do a bit of non-smooth analysis. And we're going to utilize the Frechet subdifferential and try and utilize Frechet stationary points. And so the idea here is that if my coupling function, if my thing I'm minimizing here has a coupling function which is smooth in Z, but possibly non-smooth in the W, then I can piece together the stationarity conditions for each of the partial minima by just doing a cross product to get the subdifferential, the Frechet subdifferential of the full thing. And so I can glue them together to get a Frechet stationary point of the whole problem, as long as I have smoothness in the coupling function, the thing that couples the Z's to the rest of the problem. And so the question arises, well, do we have smoothness in our coupling functions for this problem that we have? Well, our problem that we have is really a minimization of these quadratic things over a very lumpy set that has integer values. And so it's a minimization of things. But of course, I know that if my subdifferential, my Frechet subdifferential with respect to Z is non-empty, then in fact, because I'm assuming I've got an infimum, it implies that it's actually going to be a Frechet gradient. You can kind of see that the non-smoothness parts only occur kind of in this fashion. They don't occur at the minimums. And of course, I can write down the directional derivatives, both the first and the second, as my stationary point. Now I can see that if I've got strong convexity of my coupling functions, I can actually turn my stationary, my Frechet stationary point into a strict local minimum because of the nature of the function I'm minimizing. So we have these things going for us. And so that allows us to develop some theory. So first of all, we have to try and prove some convergence here. We have to look at two cases. In actual fact, there's one case that's handled very well by non-smooth analysis, and the other cases are handled quite well by kind of really arguments involving penalty functions. So it's possible that the penalty could go to infinity. And we have to handle this in the convergence thing, the convergence proof. And we have to handle a situation where I've got persistent local minima. And so what we do in our convergence analysis, we assume we have a two-block problem. The first block involves a global minimization in the X, Y's, and the W's. And the second block associated with the usual averaging that we have for our progressive hedging. And what I assume is that I'm going to only increase the penalty parameters if I don't have consensus with if my average value, my consensus averaging, doesn't coincide with the scenario-wise solutions to this problem. Whenever that occurs, I'm going to increase my penalty parameter. And this is what we do in the algorithm. And if we do that, then we discover that a lot of things happen. We discover that the the average value converges, the scenario-wise values converge. Eventually, I get the average, my scenario-wise averaging being feasible, and we get that the problem I've got here that I'm doing, the scenario-wise minimization of my function here at my current value, my local minima, has this kind of fixed point property that when I try and solve this guy, the minimums at this minimum value, the minimum occurs at that value, and that value, the bound for my persistent local minimum, is actually bounded above by the objective value of the stochastic mixed integer programming problem. And in fact, when I do Gauss-Seidel, this is quite an important point here, is that when I do this for a quadratic, and I have these persistent local minima, then I find that, well, I have a convergent set of minima tending towards this. If this family that I have, which is convergent set of local minima, are not persistent, then the ball on which I've got the local minima operating shrinks to 0. So what that means is that non-persistent local minima not only have their objective values going to infinity, but the domains on which they attract their local minima have measures that go to 0.
Això és un rotllo horrorós, però estic... No, sí, però estic xatejant amb el Michel.
Sorry?
Go ahead. It was just an accidental.
Okay. And we can also say that the Gauss-Seidel iterates converge if they are done, if they all lie within some neighborhood of this persistent local minimum, then they will converge. So this fully covers the unbounded penalty parameter case. For the bounded, by the way, just in passing, the underlying duality theorem we have is that the global minimum of my regularized function gives me the value of the stochastic mixed integer programming problem. So we have that the persistent local minima are the feasible solutions, and the global minimum is the optimal solution for the problem itself. So here we're going to do this block Gauss-Seidel thing. My G that for my Gauss-Seidel is going to be made up of a function H, which has the W's, a coupling function in the Z and the W's, which is going to be assumed smooth. And my first block minimization will be in these guys, and my second block minimization will be in the Z's. And if I were doing that, then I can write this theorem down. If I'm doing that, if I do Gauss-Seidel for a fixed row, and I get this, and these iterates converge to these values, it winds up being a solution for this problem. In particular, it's a solution for one of these sections. And in fact, it's the proof really requires me to do this global minimization in the iterations. Remember, what we're doing up here is that I'm doing in these problems, I'm doing a global minimum. I'm solving the QMIP in these variables, and I'm doing a exact local minima in the Z variables. So it's a global minimum in the W's. And so the fact I'm doing a global minimum in the W's means that in my problem, I can assume along my iterates that I have this non-zero Frechet subdifferential for the optimal WKs. And then I can do some non-smooth analysis arguments to show this convergence theorem. So in the case when I've got these squared norms, then it turns out that these solutions I get here, are these solutions here going to be a solution for my actual regularized function? Well, the answer is yes, as long as I have consensus holding at my solution point. So as long as our solution converges to a Frechet stationary point for my problem, big problem, if it satisfies non-anticipativity at that point, then in fact it's going to be a strict local minima for my whole regularized function. And in fact, I've got my smoothness required for my Gauss-Seidel to converge holding at that point. So to summarize, we must do a global block minimization in the X, Y's, and W's. I only increase the parameters, my penalty parameters, for the values which don't satisfy non-anticipativity. I also assume, and in fact, we never have to do this in the numerical problems. To get convergence, we have to assume that we do a small perturbation if a variable persists in not being satisfying the non-anticipativity constraint, because of course, we have always a chance that even though these domains of traction of these non-persistent local minima do shrink, in theory, it's possible for Gauss-Seidel to converge them, even though they don't look very attractive for a minimization problem. But if a small perturbation means with probability 1, we must converge to a feasible solution. So if we look at the experiments for our algorithm, and this is the algorithm in its full glory, if we do this, we can initialize our parameters according to the scenario-wise decoupled solutions. So the arrowed up and the arrowed down are the smallest and largest values in the solution xi that I get. And I increase my penalties by looking at the violation and non-anticipativity, and look at sort of average violation and use that to increase the penalties. Then I can look at 4 different actualizations of this. I'm going to look at progressive hedging as it is, solving QMIPs without doing anything smart. I can look at the pure version where I don't update my multipliers at all. I just put them to 0. I can look at a method where I try and update my multipliers for a finite number of iterations, which is governed by this rule. I kind of keep track of how far the consecutive ones are apart, and when things fall below a certain bound, I stop updating my penalty parameters. And I'm going to call that the dual step length variant. And then I'm going to do another one where I average the penalty parameters and I stop updating them when the averages get close to each other. And this again tries and look at when they stabilize, and I call this the running average one. And so I run these for 100 iterations of all 4 methods on the set of problems I had before. And what I find is that the one where I don't update the penalty parameters always converges faster than everything else. I put the multipliers to 0, I get a solution very quickly, but the solution may not be very good. It may not have a good quality. In the other variants where I do things, I do update the multipliers for a period of time, I get much better solutions. In fact, for the last 2 versions, I get as good a solutions as the progressive hedging method if I run it with a low value of the penalty parameter for a long period of time. In fact, the progressive hedging guy sometimes doesn't get solutions, while the other 2, in fact, always get a solution in the 100 iterations I've got. So here's some plots. So progressive hedging is the brown. With the multiplier set to 0 is the dark orange. The first version, which has updates and multipliers, is the next orange, and this is the average running one. So this is the 4 of them. When I have a shaded bar, means I got a suboptimal solution. The solid bars means I got an optimal solution, and the empty bars means I didn't get an optimal solution at all. So progressive hedging, the heuristic progressive hedging, did not converge in that case. And so you can see that the guy where I don't update the penalty parameters always converges very rapidly, but not to a very good solution. And yet the other 2 guys do eventually always converge to some optimal solution of the problem, while progressive hedging itself occasionally fails. So we're able to generate for this method, in fact, optimal solutions of these problems, despite the fact that the theory of convergence only guarantees feasible solutions. So we can, in fact, think of this whole method as being kind of like a feasibility pump type thing. We're trying to generate feasible solutions, but we're trying to generate them in such a way that we're trying to maximize the potential that we get a good feasible solution. And if we do this in a smart way, by starting from a very optimistic infeasible solution, we can often generate feasible solutions. So here are some of my references, and thank you. That's all I have to say on this topic. Thanks very much.
Thank you. Thank you, Andrew. It looks like all bridges have been built and we've enjoyed the bridges. Do we have questions from the audience? Please unmute yourself and ask your question or make comments. We have a number of people doing computational stuff in the audience. I suspect that there should be comments at least or questions.
I have one question.
Andrew, could you show us the reference once again, please, at the end?
These references.
Yeah.
Okay, well, the references, this is the duality theorem reference that I did mention that we wrote with Natasha, and the progressive hedging one. Oh, there's the augmented Lagrangian one there. There's the Frank Wolf progressive hedging algorithms, this paper here, which is the first half. The second half was about work that we're just finishing and about to submit a paper on at the moment. So we're finishing up the last draft at this stage. So we've done all the computational work and developed the theory, which is the primal approach.
Thank you.
Sorry, Matt, did you have a question?
Oh yeah, thanks, Andrew. Yeah, thanks for your talk. I have just a very naive question about something that you mentioned at the start. So your random variables are always discrete. If you had a continuous random variable, is there any methods that would be able to deal with such a thing, or is it?
No. Even continuous random variables, from my understanding, are really only solved for very toy problems. Most of the time, people try and fit a discrete distribution to the continuous one. In other words, they generate an approximation. There are actually a whole suite of methods where people try to evaluate the quality of the approximation you get. Now, there are some other approaches to solving these problems, which are based more on, for two-stage problems, there are things which are based upon kind of the, what's it called again, kind of the L-shaped decomposition technique, which is an alternative technique where they try to, if you like, fit the distribution as the algorithm goes. So there are some techniques that do that, and some people, certainly there are methods for two-stage problems where people do that, and they claim to that this is a more effective way of approaching it. But the trouble is you can't attack multi-stage variables, multi-stage problems that way. And the thing about progressive hedging, it extends quite naturally to multi-stage problems. So for multi-stage problems, as far as I understand, you really have to do this approximation of the continuous problem, the discrete problems, to get a numerical, computationally implementable method. At this time, I don't know of any other method.
Okay, thank you.
Hi, Andrew. I have a question. That may not make sense. So that may not make sense, but I'm thinking that for the algorithm you're using, is that relevant to bundle method? Because every time you do interaction, you add one more extra vectors. It's just similar to approximation in bundle method. And
that's true. I mean, you can sort of think about, if you like, the jewel of the augmented Lagrangian problem as being the kind of bundle, the proximate method, the prox point type method, So there are ways in which, certainly in the continuous case, there are quite connecting theories to these things. And in a way, if you looked at those performance curves for the Frank Wolf method, where for large penalty parameters we had this very strong convergence, that's kind of typical of what you think of ADMM. But when you look at the method of which they're doing, the heuristic method, where they're using small parameters, small penalty parameters, in a way, it's easier to understand what they're doing there by thinking about them in the way you're thinking about them, which is like as if it was some sort of proximal point thing being solved by some kind of an analog of a bundle method. So there are various ways of looking at these things, and in fact, I think, do we have our second paper here? We have another paper on this topic here, which was published at one stage by our group, where we looked at, maybe I haven't got it down here because I didn't really refer to it, where we tried to milk that kind of an analogy in order to do a version of the Frankel progressive hedging algorithm, where we actually tried to find the optimal penalty parameter as we went. Now you notice that the methods were sensitive to the size of the penalty parameter. So you can improve the algorithm by trying to somehow ameliorate a wrong choice of penalty parameter. But by doing that, you kind of introduce a kind of, what's the word, like in the bundle method, what you have is you have a serious step and a kind of a trial step, you know, and you can integrate that kind of philosophy into these algorithms as well, because you can think about them in that way.
But the convergence for bundle methods and this method is quite different, because you argue that this converges because you exhaust find a number point and then it will exhaust a search space. But then go back to the question that do you have some sort of conversion rate, like how many steps required for certain?
No, we don't. We don't have any convergence rate. That's a bridge way too far for us at the moment. To try and come up with some sort of theory which makes sense, to say that you've actually got convergence is quite a step forward, given that most of the time in the past these have just been heuristics. You know, there are a lot of things that are done in programming which are heuristics that seem to work very well, that people have no clue as to why they work. And the thing that we've found, that putting some theory around these methods, is that we've been able to understand how to deal, how to vary the parameters in the methods to make them work even better. So the kind of I guess the benefit you get from the theory is understanding better why they converge, and therefore how can you make them converge better by manipulating the levers in the methods, if you like, is what we've found, you know. But yeah, look, I'll send you that other reference on the other paper, however, because that paper is getting quite close to answering the question you're posing there, and you might find that enlightening.
Okay, thank you very much. And yeah, one last question, because I saw you mentioned here the Bender cut. So I think your method is similar to generalized Bender decomposition method, where you consider one of the problem at the dual.
I guess progressive hedging itself is somehow related to that too, isn't it? I mean, it is trying to. They both try and use the structure of the problem, right? You've got a complicating constraint that you're trying to deal with, which couples all these scenarios together, and you're trying to find some way of doing a two-stage thing where in one stage you kind of decouple through the scenarios, and Bender's decomposition is trying to do that as well by the mean, you know, by it's exploiting that structure, the L-shaped structure of the problem.
Yeah, thank you.
Yeah, I agree. That's true.
Thank you, Andrew.
Okay.
Okay, thank you, everybody. Thank you, Andrew. We are already a little bit over the time limit. Maybe one very short question, if someone is willing to ask. Do we have a very, very short question? No, it looks like everyone has only long questions. So thank you very much to the speaker, to the audience. As far as I know, we are going to have a break in our seminars for the winter in our part of the globe, or for summer in the Northern Hemisphere. And the continuation of the seminar will be announced on the website. Okay? Thank you very much. Applause.
Thanks very much.
Thank you.
See all of
Thank you, guys.
when we continue sometime in the future, possibly in a month.
Everybody stay safe.
Thank you very much.
Thanks.
See you next
Stay
season.
safe, everybody, indeed.
Thank you, everyone.
Thank
Thank
you,
you, Andrew.
everybody.
Very good talk.
You all take care.
Very much.
let's enjoy the pictures of each other. And
Yeah,
have a
that's
break.
right. I mean, we can all have a little chat. I haven't
So-
seen you, Michelle, since Vietnam. In better
I hope-
times.
I hope you don't mean the Vietnam War.
No, no, no. We were in Vietnam what was it, about 3 years ago now, wasn't it?